levels in atomic hydrogen. And at the moment, what I've put up there is the energy level diagram for atomic hydrogen. And I've put the lines that, the line emission that results in visible region photons. Okay? Turns out, of course, well, not of course, but it turns out that it's not just these visible region energy jumps that can happen. There's other energy jumps that can happen also. So I'll say something here about that. These are the transitions. Remember, we call these energy jumps transitions. Or the photon energies, photon frequencies. That result in a result because of these are the transitions or the photon frequencies that result from the visible region. I haven't written this very well. These are the transitions or the photon frequencies that result from the energy jumps corresponding to visible region photons. I know it doesn't sound great, but there it is. This is an energy level diagram for hydrogen. Now, when I say hydrogen, I mean atomic hydrogen, so not the molecule hydrogen. This is just an atom of hydrogen. In fact, it's not just those energy levels that we see, those energy jumps that we see. We see quite a few more lines. And here they are. Boys, quiet, please. Hasik. Thank you. So here we have, this is Barmer region here. So Barmer series, these are visible to ultraviolet. Passion series, here the infrared, so we can't really see these and they wouldn't be shown on our spectrum chart. Over here on the right hand side, the ultraviolet region of the spectrum, we can't see these either. Now, if I were to draw an arrow here pointing that way, what's going on with the frequency as you move from left to right? Frequency decreasing. Infrared to visible to ultraviolet. Frequency increasing, yes. And so by E equals HF, energy increasing. Energy increasing also. Okay. And that's from left to right. Now, let's have a look at up here. Now, I was drawing transitions because I wasn't being very specific about the transitions that are possible the other day, really. But now I'm going to be more specific. If I were to draw a transition from there to there. Okay, what we would see is that transition is going to result in some energy being emitted by the atom as the electron jumps down an energy level. Now that's quite a big jump. That's the electron going from there to there. That jump corresponds to 10.2 EV. Hope everyone can see. 10.2 EV exactly. Let's have a look at what 10.2 EV is. Now I bet most of you could do this. 10.2 EV is equal to 10.2 multiplied by the electron charge. If we're changing it to joules, which equals 1.63 by 10 to the minus 18 joules. Now, E is equal to HF. So F, from that we can get F is equal to E on H, which equals the energy, 1.63 by 10 to the minus 18 over 6.63 by 10 to the minus 34 2.46 by 10 to the power of 15 hertz. Probably doesn't mean much to us at the moment. What if we convert that to wavelength? C equals F lambda. When we're talking about light, lambda is equal to C on F, which equals 3 by 10 to the 8 meters per second, all over 2.46 by 10 to the 15 that equals 1.22 by 10 to the minus 7 meters. Now, what do we know about that? That might look a little bit more familiar. That's a pretty small wavelength, isn't it? As far as the visible region, from what we know, 400 to 750 nanometers. 400 nanometers to 750. Is that our? That's the visible region approximately. A little bit more, a little bit less. What's this? It's a little bit smaller, isn't it? Yeah, it's UV region. So what I've said is, and what I've shown here with a couple of calculations, is that this energy jump here, 10.2 EV in atomic hydrogen, corresponds to a UV ray photon. Okay, so that's going to be must result in a UV ray photon. We can't see that jump, and it's not going to show up on a spectrum chart. Yes, Paul?
So if the jump was smaller,
yes,
that means the energy would be smaller.
Yes. Smaller? Yeah, that's right. So these little jumps here that I'm drawing here, actually, not that one. This one here. These jumps that I'm drawing here, except for this little one here, that one's a little bit too small. These two jumps here, and there are others, result in energies that are small enough that the frequency is small enough that the wavelength increases just slightly. And when the wavelength increases, we end up with these visible region spectrums. I don't know which one they exactly correspond to. We could do the calculation if we wanted to. That jump there, uh, minus 0.85 minus 3.40. If I take away those two numbers, 3.4 minus 0.85, I'll end up with the change in energy there. And I can very easily work out from that change in energy what wavelength results here. Okay? But I'll just show you the picture. I'll just show you the diagram here. We call them the Lyman, the Balmer, and the Passion series. Passion, yeah. So, oops. Oh no, what have I done? Okay. So, if I just make this a little bit smaller first, that'll be okay. Have a look here. The Lyman series, big jumps. We've just shown there that jump, that minus 3.4 to the minus 13.6 EV down to the ground state results in a UV ray photon. All of these will have minimum UV ray photon. Balmer series, there's one missing from the Balmer series there. This diagram's not quite right. Now, the Balmer series here, most of these result in visible ray photons. Oh, actually, I've missed. Yeah. Okay. Yeah, all right. I'll do that again. Doesn't look that good, does it? No. Here we go. So, Balmer series, all but one result in visible region photons. The Passion series, Passion, I don't know how you pronounce it. I always say Passion. These result in UV ray photons. Infrared photons. Now, these are smaller energy jumps, bigger energy jumps again. So let's say that, or let's write that. All transitions to the ground state result in UV photons. Hydrogen only. I'll say something about the ground state as well in a second, and because we have to clarify that a little bit too. The 4 lowest energy transitions to the first excited state boys, please, result in visible photons. So the 4 smallest jumps, this one, and this one, result in visible photons. This guy here, UV. Okay, we can't see that one, that transition there. I might have to go to black hole, and I'm going to ruin the diagram here. transitions to the second excited state. These ones here, the Passion series, result in infrared photons. You do need to know these for the exam. You do need to know what they are called, the Lyman, the Balmer, and the Passion series. It's something that I haven't managed to learn. I don't know why. It's just one of the things I haven't picked up after all the years of teaching. I mean, I may know it now. It's just, yeah, I haven't committed it to memory because I've always had the diagram in front of me. If you don't consciously decide that you're going to learn it, sometimes you don't learn it. Okay, so what's that, Anthony? No, you don't. No, it's not necessary. It's not necessary to remember these numbers here, but it is necessary to remember the Lyman series result in UV ray photons. Balmer, mostly visible photons. The Passion, infrared photons. Okay. Okay. So next thing, how does this happen? Continuous spectrum, spelled it wrong. Here's the continuous spectrum. How do we get one of those? That there. This is a line emission spectrum, and we know that that's like the fingerprint for some element or compound, chemical. This is the continuous spectrum, though. Where does that come from? What would that be if I mixed them all together? White light, wouldn't it? Okay, so how do I get white light? How do I get a continuous spectrum? Has anybody got an idea? How do I make one of these? You can view it through we could say that we're looking through a spectroscope, but how do I point this? What do I do such that I can point a spectroscope at it and see that? Point it at the sun, okay, but what's going on in the sun? Everything, okay. Here I have a metal bar, solid piece of metal, and what do I do to that substance there to make it emit the continuous spectrum? Heat it up, don't you? What are you doing when you heat something up? Yeah, that's right. So what we'll say, we'll give it some infrared radiation, and we know that there's a chemical reaction that we're all quite capable of making. That chemical reaction is where we burn things. So we burn some stuff. That's supposed to be my flame. I know it's a bit stupid. It's not a very good flame. But what's that? Yes, there is. Yeah, yeah. Well, you can ask a question though. So I apply heat to this piece of metal. What happens if I just apply a little bit? No, actually, what happens if I had a piece of metal in my hands in here? What's going on with that in that metal? Vibration there is. In fact, the molecules that make up that metal, whatever that is, we draw them as these group of atoms all lined up next to each other. And we know from physics that they've got, and chemistry, that they've got electrons buzzing around. I'm just going to draw one on each. This metal isn't made of hydrogen, and uh, and we know that these electrons kind of have energy levels around those on the protons and neutrons that make up the nucleus. And we also know, and we've heard this before and nobody's brought it up yet, but that they kind of vibrate backwards and forwards, and they've got spin and all sorts of stuff. And you can't and what we do is when we add heat to it, we cause the energy levels in these atoms to increase, and therefore their vibrations increase, and their vibrations, of course, have a frequency. And the frequency of vibration is such that they don't like to be in that excited state all the time. What they do is they jump back to lower energy states, and their frequency reduces. And in order to do that, they emit some light or some heat or UV radiation, whatever you want to call it. It's just light. So if I add heat to the molecules that make up that metal, I cause them to vibrate faster. When I cause them to vibrate faster, imagine if we were sitting here in a dark room and I heated a piece of metal up with my hands. You know, when you pick up a piece of metal, almost always it's cold. But if I held it for long enough, it would be a very similar temperature to my hands, at least where my hands were anyway. What I've done is I've caused the frequency of vibration of the molecules that make up the metal at the point where my hands are touching it to kind of reach an equilibrium, and so they're vibrating faster. But not fast enough that we could sit here in a dark room and we could see it emitting light. What do you have to do? You have to add more heat. You add more heat to that metal, and there would come a point where it would start to emit infrared radiation of its own. You could hold it up next to your face and you would feel that light hitting the side of your face. You couldn't see it, but you could feel it. The light was being emitted, okay? We can perceive that infrared radiation. If I add a little bit more heat in a certain area, yeah, I'm going to make it start to glow very deep red first, okay? And as I add more heat, it's going to become brighter and brighter and brighter into the oranges and yellows, and eventually white if it doesn't melt, okay? And all these atoms dissociate, but eventually white light. And what's going on when it's emitting white light? It's all the frequencies. Those atoms now, at that point, are vibrating with so many frequencies that we see it, we perceive it as all the frequencies put together, and all of those frequencies put together make up white light, which is what we get when we heat up a tungsten filament by passing a current across it. Tungsten has a melting point of around, I think it's about 4,000 degrees, which is very useful because it doesn't dissociate as we add energy to it. And as we keep adding energy to it, it goes whiter and whiter and whiter, such that we can have the old incandescent light bulbs. And they're still a yellow color, but they're pretty white. They emit most of the region of the visible spectrum, most of the colors of the visible spectrum. Okay? So all this is caused by these vibrating with a certain frequency atoms that make up the substance that is causing this continuous spectrum. Okay? What's happened here? Oh. Better? So I'll say something about it because I already asked the question. I wrote the question as the metal is heated, the atoms vibrate with such a range of frequencies that we see all or almost all of the colors of the rainbow. Oops. Colors of the rainbow. Which is just a continuous spectrum. One last thing today. Fluorescence. Now, I thought I had some here, but you've all seen nappy sand. You know what nappy sand is? In order to get your clothes or your shirts in particular very white, we need to play a trick on you or on your mums. If she does the washing, that is. Maybe your dad does the washing, I don't know. I'll bring some nappy sand in. I have to do my own washing. I'll bring some nappy sand in. We'll look at it under UV light, and you'll see something interesting. This whole idea, the ads that you see on TV on for all of the soap powders that, and they say that you get whiter whites. It's all a trick. What happens with white clothes eventually is they go a yellowy colour. What we essentially do is we wash them in these soap powders, and the soap powders have a substance in them that fluoresces under UV light. And so when sunlight falls on your white shirt, they fluoresce, just the smallest little amount of them fluoresce, and we see it as very bright white light. Okay, so I'll bring some nappy sand in, and you'll be amazed if we can find a dark room on the day. I'll put on a black light, and it'll be very dark in here, and you'll see it light up. It's amazing, yeah, it's amazing. And got little chunks of really bright stuff in it. Yeah. Nothing against nappy sand, but it is a trick. All soap powders. I'll actually bring some of the stuff in. So this stuff here, if you put it under UV light, it just looks like a white powder of some sort. It'll fluoresce. What is fluorescence? Who's got an idea of what fluorescence is? Shh, please. Dylan. Shh. Yes. Yep, absolutely. So let's, what's this telling me here? Battery is low. Okay. I might run out today. We'll see how we go. I'll get an energy level diagram up for you first. Here we go, fluorescence. So Jack's got it right exactly. Oops. There it is. What's going on is that we shine in, well, what are these? Here's hydrogen again, and hydrogen won't tend to fluoresce, well, not in the situations that I know of anyway. What sort of light do you have to give hydrogen in its ground state to get that one jump there? Has to be UV, doesn't it? We know that now. To make that 10.2 jump, that 10.2 EV jump, we have to send in UV light. Okay, UV, which we can't see. Now, if we can't see it and we shine that light on the hydrogen, and then when it's going back down to it, on its way back down to its ground state, it jumps a couple of shorter jumps. What are we going to see? What will it appear to be to us? It'll what? Yeah, we're going to see regions of the visible spectrum, aren't we? So what it's going to look like is we're not shining anything on it at all, and yet it emits more light than is shone on it, so to speak. Okay, so what we would see is this black light, UV light, and visible region spectrum coming out. We call this fluorescence. What's that? Yes? We shine, this is just a bit of hydrogen, and we're still looking at hydrogen. I don't know the situation in which hydrogen fluoresces, but we shine on UV light onto that hydrogen, this one atom of hydrogen, and imagine we can't see that UV light. It looks like a black light to us, essentially. So it's not very bright in a dark room. And what happens is, on its way back down to its ground state, it stops. It does smaller jumps. What is it? What happens if it does those smaller jumps there? If it only does that jump, it's got to emit a photon. If it only does that jump there or that jump there, it's got to emit a photon. Or the little jump there, it's got to emit a photon. These jumps here correspond to visible region photons. And so what we see, the way we perceive it, is very little light going in, or UV light, ultraviolet light going in, and white light coming out, or bright coloured light coming out. Okay? No, yeah, those transitions are possible, but they will tend to, some of the atoms that make up the substance, because remember if we've got a gas of hydrogen, we've got lots of atoms, and when they jump back down, they don't necessarily jump all the way back down. Some of them will do this jump first, or that jump, and there's trillions of them in a very small amount, and they all do lots of different transitions. Okay? I'll say, if the atom is excited with UV photons, it will not necessarily re-emit, I think I'll say, re-emit UV photons. To get back to the ground state. It may, or they may, make more than one transition to get give me here, yeah, it is. To get to the ground state. in doing this, the transitions may correspond to visible photons. One thing I do have to say is if I have a UV ray photon come in, the transitions, no matter what it takes, what transition it does to get back to the ground state, they must add up to the original photon. We can't have extra energy coming out or extra energy going in and losing some energy in the transitions. It doesn't happen. The sum of the energies of the transitions must equal the energy of the original photon. Yeah, that's a perception thing. So why do fluorescent things happen to have a glow to them? It's a perception thing. What they appear to be doing is emitting more light than is landing on them. And we find that as strange in our perception. Okay, so you can see here, we'll have a look at the nappy sand and it will all become really evident because I'll have a UV light and the UV light does emit light. It emits some visible region purple light, but it also emits higher energy light as well that you can't see, and so it seems very dark. So we'll have it in a dark room and I'll have the black light on, holding it over the nappy sand. It'll look like there's not much light at all, but the nappy sand will be bright. Yeah. It would look normal, yes. Yes. All it is we have experience with visible light. So we have a lot of experience with sunlight and the lights that light up the room and the artificial light that we live in. And we know how much things tend to reflect, how much of the visible region spectrum things tend to reflect. And when we take something, a substance that tends to reflect more because it does this energy level thing where it fluoresces, our brains say, hang on, that looks a little bit strange to me. That's not what I was expecting. I was expecting less light to be reflected from that substance than is actually being reflected. It's just a perception thing. That's a good question. I don't know. You'd have to ask a biologist. So that would be quite interesting. It probably hasn't happened in the last couple of thousand years, and we wouldn't have measured. The earliest that we would have measured how much people perceive would have been the last couple of 100 years, I imagine. So we don't know. I can't think of any way there might be to tell. Something to do with the colour of the foods we eat or the flowers that we pollinate. So the bees have evolved with the flowers, and the flowers have evolved to be really attractive to the bees, and so maybe we could have a look at animals in history and how they've evolved to see things, whether the region of the spectrum that they experience is getting greater. I don't know. Yeah, don't know. Good question though.